The global ocean is an immense, volatile, and deeply hostile physical environment for any kind of precise data collection. Isolating a few parts per billion of a chemical anomaly within millions of cubic kilometers of constantly moving fluid poses a massive engineering paradox. Relying on a single type of sensor to act as a universal detector is geometrically and physically impossible given these spatial extremes. This 3D wireframe grid maps a necessary solution. Marine monitoring requires a multi-scalar data acquisition architecture that bridges microscopic analysis with global macro observation. The first layer of this architecture occurs locally, conducting real-time in-situ profiling directly within the water column. The second layer moves ex-situ, utilizing coastal laboratories to perform definitive analytical chemistry on physical samples. The third layer scales that data collection outward, deploying autonomous robotic platforms to patrol wide regional areas. The final macro layer watches from above, providing global observation through satellite remote sensing. Effective marine monitoring relies on a cohesive system that treats the ocean as a continuously observed, multi-tiered environment. We begin at the foundational level of data collection, capturing immediate metrics inside the local water column. This cross-section illustrates the CTD Profiler. Descending, it plots real-time 2D graphs, tracking depth against temperature and salinity. The conductivity sensor measures precise salinity levels. Mapping these gradients identifies exactly where polluted freshwater runoff mixes with denser seawater. Alongside the CTD, dissolved oxygen, or DO sensors, target a critical ecological threshold. DO sensors detect hypoxia, alerting scientists to expanding dead zones. These low oxygen areas are routinely triggered by eutrophication, where excess nutrients from agricultural or sewage runoff consume the available oxygen. Nephelometers, more commonly known as turbidity sensors, are deployed to measure water clarity. Sudden spikes in turbidity serve as physical proxies for heavy sedimentation, dredging runoff, or severe algae blooms. Simultaneously, pH meters continuously monitor ocean acidification, tracking shifts exacerbated by both atmospheric carbon absorption and localized coastal chemical discharges. To detect biological hazards, the array utilizes fluorometers, which perform a highly specialized optical function. This fluorescence emission graph isolates this distinct peak, the exact absorption signature of chlorophyll A, providing a real-time proxy for phytoplankton biomass. When these readings surge, the data directly signals the formation of harmful algal blooms, known as red tides. The in-situ layer operates on a strict trade-off. These sensors deliver immediate, high-resolution physical proxies of the water state, but they lack the specificity to identify complex chemical toxins. To achieve that specificity, the focus shifts from the open ocean back to the highly controlled setting of a coastal laboratory. Scientists must physically capture water from the site to secure the definitive chemical signatures that field sensors simply cannot process. Specialized devices like Niskin bottles or rosette samplers are lowered into the water column and triggered at specific target depths to trap highly isolated samples. Once ashore, the process transitions from measuring physical proxies to utilizing highly sensitive analytical instruments. This data visualization details gas chromatography mass spectrometry. The gas chromatogram isolates compounds over time. Zooming into a single peak reveals the mass spectrum, identifying the complex organic compound. GCMS is essential for identifying complex organics, like petroleum hydrocarbons, PCBs, and pesticides. For inorganic pollutants, labs rely on a distinct method, inductively coupled plasma mass spectrometry, or ICP-MS. ICP-MS is the industry standard for analyzing marine water and benthic sediments for heavy metal pollution. It operates with enough sensitivity to pinpoint trace concentrations of mercury, lead, cadmium, and arsenic. Finally, labs deploy spectrophotometers, which utilize light absorption rather than mass spectrometry to analyze samples. Spectrophotometers are calibrated to pinpoint specific nutrient concentrations, mapping the exact levels of nitrates, phosphates, and ammonia that act as the primary drivers of coastal pollution. Coastal labs deliver precise chemical identification, but the necessity of manual sampling and physical transport creates a spatial bottleneck, making this layer too slow for a real-time crisis response.
That spatial bottleneck limits the scale of observation. Human crews on research vessels simply cannot manually drop sensors or collect water samples continuously over millions of square kilometers. The solution is to integrate the rapid in-situ sensors directly into autonomous robotic platforms. Autonomous underwater vehicles, or AUVs, and ocean gliders carry these chemical and physical sensor payloads deep into the water column. These platforms possess extreme operational endurance, capable of functioning in harsh or remote marine environments for months at a time without any human intervention. Tracking this 3D isometric grid shows an AUV's undulating flight path. Moving in a continuous dive and surface pattern, it leaves a volumetric colored trail. This yo-yo pattern generates continuous 3D water quality profiles, tracing chemical plume density directly back to its source. While AUVs match to volume, smart ocean data buoys serve as their stationary, anchored counterparts at the surface. These floating platforms act as marine IoT nodes. Equipped with weather, acoustic, and water quality sensors, they transmit continuous, real-time telemetry back to shore facilities via satellite communication. By integrating sensors into autonomous hardware, the architecture transforms isolated static data points into dynamic, continuous 3D regional maps. To push the scale of observation from regional underwater robotics to the macro level, the architecture relies on global satellite networks. Remote sensing is the only technology capable of monitoring vast stretches of the ocean surface and instantly spotting large-scale disaster events as they happen. This high-contrast satellite readout demonstrates synthetic aperture radar, or SAR, which is primarily deployed for oil spill detection. The smooth dark patch represents a clear anomaly against the textured ocean surface. SAR operates by bouncing radar waves down to the water to detect minute changes in the ocean's surface capillary waves. When oil accumulates, it physically smooths these capillary waves. The flattened surface reflects the radar energy away from the satellite, generating the distinct dark spot signature seen on the readout. Alongside radar, satellites and unmanned aerial drones utilize multispectral and hyperspectral imaging. These imagers function by detecting subtle shifts in ocean color. As seen on this 2D coastal map, the spectrum band analysis isolates specific light wavelengths reflecting off the water. Mapping these color shifts identifies boundaries of massive suspended sediment plumes or algal blooms. Hyperspectral imaging is now being tested to isolate the specific spectral signatures of large plastic debris accumulation zones drifting in the open ocean. Remote sensing acts as the macro trigger for the entire network. It spots massive surface anomalies from orbit, directing the underlying architecture exactly where to investigate next. This composite network model unifies the 4 distinct layers into a single data architecture. A satellite detects a surface anomaly and beams the coordinates down to a surface buoy. The buoy relays commands to an AUV below it, and data packets stream continuously to a coastal laboratory. The diagnostic workflow is fully integrated. Remote sensing spots the macro anomaly from space. Autonomous vehicles mobilize to map the 3-dimensional spatial extent of the plume underwater. In-situ sensors capture the real-time physical proxies of the event, and laboratory instruments finalize the process by delivering definitive chemical identification. The current frontier of marine engineering is focused on eliminating that final laboratory bottleneck by pushing high-specificity chemical detection directly into the field. Advanced optical microplastic sensors, utilizing Raman spectroscopy and flow cytometers, are currently being adapted for deployment on ships and buoys to physically count plastic particles directly in the water. At the chemical level, engineers are deploying biosensors. These devices use living organisms, enzymes, or antibodies to detect specific pathogens and toxins with extreme sensitivity. These biological molecules are engineered to generate an immediate electrical signal the exact moment they interact with pollutants like heavy metals, bypassing the coastal lab entirely. The future of marine protection lies in this unified architecture, an increasingly autonomous, interconnected web that provides high-resolution data across the global ocean.